Excellent. Right, so before we dive into the wonders of Sobolev spaces and weak integrals, which is what we're talking about today, I did promise at the end of last lecture there was one small loose end that I would tidy up. So we got as far as actually implementing our one-dimensional finite element problem on the whiteboard, and we had a strong boundary condition sitting on the end, and I promised I would briefly sketch how the implementation of that works. We will come back and do something really more significant about boundary conditions once we've talked about how you do nonlinear problems a little bit later in the course. But I will look at this one for the moment. So if you recall, we're in the situation where we've got our domain, and on each element in the domain, we have a local indirection map. So that means that when we assemble the local integral, we get a little 2x2 system, and the little 2x2 system then gets inserted or added to the large system at the corresponding points. So if this were points 0 and 1, then this little matrix goes into this corner here, and then when we do the next element, we can put the next matrix in, and so on. And that's all really good, except for the minor detail that in the problem we were solving, there's a Dirichlet boundary condition on the left-hand side here. So in the function space that we're testing with and looking for a solution in, there isn't really a test function here at all. This one kind of doesn't exist, and the function space starts from here, because that's how we enforce that the solution was 0 at this end. And what that means is that what we really wanted to end up with in our matrix here is 1 here, and 0s are all the way across the here, and 0s all the way down there as well. So what do we do? So one thing we could do is, when we are assembling this little local thing here, we could notice that we're assembling something that's going to go on the boundary, and we could put those in there. And that's actually how Phoenix does it in the vanilla case of Phoenix doing things. So that's one way of doing it. Another way of doing it is to more or less do what I just did here, which is to assemble the matrix as usual, ignoring the fact that this one's a boundary condition 1, and come back and then say, oops, I didn't really mean to do that, and overwrite the entries. The reason that's problematic is normally this is a sparse matrix, and it's a sparse matrix which is stored in compressed sparse row format. And so it's very easy in compressed sparse row format to go find the entire contents of a row of a matrix and muck about with it. However, it's very, very difficult to find the entire contents of a column of a matrix. That's not explicitly stored everywhere. You essentially have to do a search on the data structure to find where it is. And so that's an unattractive option. The final option is, it turns out you can just 0 the row and rely on the solver to put the column in for you. However, the problem with that is if you thought your matrix was symmetric, well, it ain't anymore. So if you thought you were going to use something like conjugate gradient as your solver, you probably weren't anymore. So that's really, really unattractive. The final option is what we do, which is we muck with the indirection map. So what happens is, when we know that we're assembling into a function space which has boundary conditions, where those boundary conditions apply, we change the indirection map. So that if you look up, in this case, I, so I was, well, actually we call it K. K is our indirection map, and K takes which element we're on. So if we're on element 0, and we put in 0, so remember in local numbers we've got a local 0 and a local 1 here. Without the boundary conditions, we'd expect that to return 0, which is the global index of this node. However, what we do is we muck with the map and we get it to return -1. Or in fact, minus anything else. In the extruded case, it's a little bit more complicated, but a negative number. The reason we do that is that there's a handy feature of PETSI, which is the thing we use to assemble our matrices, which is that if you tell PETSI to insert into a entry in your matrix, and either the row or the column you specify is negative, it just throws away the number. It doesn't do the insertion. And so when we do this, what happens is we take this small matrix and we put things in here, but we're actually asking it to insert into the block which looks like this. And so what Petsy does is it puts that value in correctly, and it throws away these three. And that's almost exactly what we wanted. The problem is that we now haven't added anything in there. And then what we do afterwards is we afterwards go through and we set the diagonal on all the boundary condition nodes to be 1, which is a straightforward process. On the right-hand side, we do something slightly different. On the right-hand side, we don't have this problem with needing to address the entries in the vertical. So on the right-hand side, we just tell the system to go right ahead and assemble the right-hand side as if there wasn't a boundary condition in there, and it puts the boundary values in there. And then what we do is afterwards, we go back and we clobber these values, and instead of having whatever the value of the integral is, we put the boundary condition value back in afterwards. And that's easy because this is just a vector, so it's very easy to insert into any point you like in that vector. So that's how that works. Right, so that's the end of the catch-up from last week of stuff I didn't quite get to. And after last week's practical lecture, we're going to get all mathematical again. And the objective today is to understand how it is that it can possibly make sense that we are taking derivatives of functions which are not differentiable. Because the typical finite element functions we use have corners at the edges of elements. So we need to understand why that's true and what it is that we need about our function spaces so that we can use them in different sorts of derivatives. And so this is a sort of mega simplified version of the really advanced theory that Colin Cotter's involved in the finite element exterior calculus, where you are proving these spaces and having a mathematical structure that works in them. But it's very useful for understanding why you are and aren't allowed to do certain operations in the finite element space. So in order to do that, we need to dive into a bit of maths. And in your lecture notes for today, there's a section at the front which says Review of Lebesgue Integration Theory. So somebody should report that particular heading to advertising standards because it's really untrue. Because it doesn't even provide a definition of a Lebesgue integral. Fortunately, we don't care. So there is a important technical difference between a Riemann integral, which is an integral which works the way you learned at school, where you carve the domain of the function up into little strips and you make the strips thinner and thinner and thinner in order to do the integral, and a Lebesgue integral, which is more or less the other way round, where instead of carving the domain up into vertical strips, you carve the range into horizontal strips. And there are circumstances in which that really matters. Essentially, none of those circumstances matter to us at this point. So as far as we are concerned in this course, these are Lebesgue integrals, but they're just integrals. So you don't need to worry about how to do that. There are wondrous and huge resources out there for people who want to go into the theory of that in more detail. We are going to need a few things, though. So the first one is we're very used to taking this particular norm of a function, right? So this is what we've been doing every lecture so far. So that particular norm of a function is the integral over whichever domain we're currently interested in of the function squared dx, and we take the square root of it, or for reasons that are about to become very obvious, I will choose to write that as right power of a half outside there. So it turns out that not only is that a norm, but it's a norm if we replace 2 by any other positive number. There's a slightly more general sense, and if you read the back of the chapter that we're not going to do, there's even a sense in which you might be able to do that with a negative number. We're not going to talk about that now. So let's just deal with that. So I put traditionally P in there, and that means that I put a P in there. So I need the absolute value sign in there in order to make all the properties of positivity and triangular inequality and things come out, because remember, that might be an odd number. It might be 1, at which point that matters. And I put a P up there. So that I claim, but I'm not going to prove. They do prove in the notes. We're not going to go through that in that much detail. That I claim is a norm in the sense that we discussed previously. So it's positivity-based triangular inequality. It scales by scalars in the correct way for a norm. But an interesting thing to notice about it is when we introduced norms, we first introduced inner products. And then we said, okay, if I have an inner product, I can make a norm out of it. So if I have some sort of inner product of A and B, then I can always make a norm by taking the square root of A and A. And that's how we got L2. So L2 is a norm induced by the L2 inner product. That's unique here. Right? It is important that that's a square root and there's 1 over P. There's not really a sense in which the other norms in this space come from inner products. So that's one of the reasons why the L2 one is the one that turns up an awful lot. But there are a couple of other ones that are really important to us. So one of them is the case 1. So L1 is the case of functions whose absolute value is integrable, and then you take the 1 over 1th power, so that you do nothing to them. And the other important case is normally infinity is not a number. In the mathematical sense, the computing pedants in the room will understand that not a number and infinity are different, but it is the case that in this particular circumstance, that makes sense, although it doesn't really make sense to write an infinity in here or a 1 over infinity in there. But if you took the relevant limit, took the limit as p went to infinity, you would get something, and you would get something which has the properties of being a norm. It's called the L infinity norm. And the L infinity norm is, get the notation right from the book, it's the essential supremum. Don't worry, scary new words, we'll discuss what those mean in a minute, over the set of absolute values of the function for any x in the domain. So what that basically means is if we were to call that max instead of essential supremum, then we'd understand what this means. This means that it's the single point at which this function takes its greatest in magnitude value. And that works. The reason why that is not actually quite the same thing is that in these Lebesgue spaces we're interested in, we're basically defining the spaces by integrals. And remember, all of the ones up to L infinity were defined by an integral. And an important feature of the integrals that we're using all the time is the fact that the value at isolated points doesn't matter. So if I have some function which is behaving perfectly normally up to some point, and after some point, and suddenly that value is up there, in the family of norms we're looking at, we wouldn't want that individual value to change the value of the norm. That would muck the whole theory, and it definitely wouldn't be the limit of the previous sequences. So what we want is that would be the L infinity norm of this function, right? That's the biggest absolute value that it obtains. And we want that to still be true if we muck with individual values elsewhere. And so what the essential supremum is the it's the upper bound of the maximum value over any set that actually has size. So any set not of measure 0 in the technical math sense. So what that means is that I can take a family of sets around here and they all have non-zero size, and the upper bound of that series of sets is this point. Whereas around here that's not true, because this thing is only non-zero at a certain measure 0. So that turns out to be important. So that's what L infinity means. For most circumstances, what that means is the maximum value, right? It means the maximum value subject to our normal rule that we ignore anything that might happen at an individual point where it goes nuts. And as they point out in the notes, because we're only interested in solutions in integrable cases in the integral sense, we identify functions which differ only at isolated points. So if f and g differ only at individual points, we say that f equals g. They are the same function as far as we're looking at. We're kind of looking at functions through special glasses that can't see individual function values. And so when we look at those two functions, we just see the same thing. And that turns out to be sufficient for our purposes. So there's now a whole bunch of proof in there about particular properties of this space, in particular that they prove things like completeness. So this is this property that if I take limits of functions and I stay inside the space, we're just going to skip it. Right, so there's a lot of mathematical theory in there that sort of matters intensely if you want to prove things about the finite element space. Space is involved, but in terms of understanding how these work in the finite element method, we don't need to do that. So we're going to jump on to generalized weak derivatives, which is section 1.2. And this is the point at which we start to address the question of how on earth it is that we can possibly take derivatives of things that aren't differentiable, which is the whole sport in all of finite element, right? So it is kind of the whole point. And before we quite get to that, we need a piece of slightly more convenient notation, because we, especially in more dimensions, there's actually a complicated mess of derivatives you can take, because the derivatives we're interested in are partial derivatives. And so you can take, in one dimension we can take the first derivative of the function. In more dimensions we can take the first derivative of the function in any direction. So far so uncomplicated. But now I can take second derivatives, and that means I've taken two derivatives, and that could mean I take the derivative with respect to x twice, or I could take the derivative with respect to x and y once, or y twice, and so on. And when I get to taking more derivatives, there's a combinatoric explosion of different derivatives that I can have taken. And we want to be able to talk about all those cases, and we want to be able to talk about all those cases without writing out page after page of really horribly tedious, repetitive notation. So at this point we introduce some syntax, and for people who work in Phoenix land, this is syntax they use everywhere, which is the syntax of a multi-index. So a multi-index, which they're going to call alpha in the relevant circumstances. So alpha, a multi-index, is always a tuple. So what does that mean? It means it's a list of numbers and it's a list of numbers n long, where n is the dimension we're in. So we're in Rn at the moment. So if we're in
a list of numbers n plus 1 long.
Oh, I'm terribly sorry. Does that make you happier now? Okay. And so what that's going to enable us to do is to notate all the different sorts of derivatives we want to take. The length of A, which we will, out of alpha, we'll notate in the normal length notation, is equal to the sum over n of alpha I, because that's what's going to be going on, right? So if we're taking any sort of thing in the family of second derivatives, any sort of second derivative, what that means is that the sum of these is 2. So we might have a 2 somewhere and 0 everywhere else, which is going to mean we're taking the second derivative with respect to one variable, or we might have two different ones. And there's a sense in which those are all second derivatives. So this length here is a useful concept because it tells us what sort of derivative we're taking. And so if we are now in a convenient function space. So if we take some function in, for the moment, let's say C infinity, so that means things I can differentiate as many times as I like, so that I can say that this notation makes sense in every case. Obviously, I can use this notation in more restricted function spaces than that, but it may or may not make sense to take the derivatives that you're writing down. And what we are going to say is that the notation d alpha of phi, or equivalently the notation d alpha of phi of x, where I'm saying which variable I'm taking the derivative with respect to, or equivalently the normal partial derivative notation, or equivalently the superscript notation for derivatives, which is that you put a superscript in brackets, and that means take the nth derivative, or equivalently just a partial x sign with the alpha. By all of those notations, we mean the alphth partial derivative, and the alphth partial derivative is just the alpha dx. Actually, I'm going to shift my notation because I don't. I was in computer science notation. I noticed they're using math notation, so we're going to count from 1 for a while. So. So what does this mean? This means the alpha first derivative with respect to x1, which might be, if the first entry in alpha was 0, which means don't take a derivative with respect to x1, that's what that would mean, the 0th derivative. And then composed with the nth derivative, the alpha second derivative with x2, and so on. So it's a way of stacking up all of the derivatives I could possibly take. So if we take a simple example, let's take alpha equals to 0, 1, so we're in R2. That just means the phi dx2. Right, it's the 0th derivative with respect to x1 and the first derivative with respect to x2. Similarly, if I wrote 1, 1, that would mean the derivative of the second derivative in some sense of phi with respect to x1 and x2. If I didn't write 0, 1, but instead wrote 0, 2, that would mean the second derivative of phi with respect to x2 both times, and so on. So this is a shorthand syntax notation that enables me to write down lots and lots of different derivatives, and the order of the derivative is the length of alpha. That's the overwhelming story. Okay, the next concept we're going to need, so that's a file that concept. That's a notation that we're going to use in order to understand what derivatives mean. So now we're going to go on to the next concept, and the next concept is the concept of the support of a function. And this is a very useful concept in finite element, and in this particular case we're going to use it as a useful concept to define some derivatives as well, which is a sort of related but somewhat different concept. And so the support of a function is at least for a continuous function, is the domain, or the closure of the domain technically, the domain on which the function takes a value other than 0. So this matters because we are often concerned with functions which are 0 in most places and only come to be not 0 in a small area. So, for example, if we take our normal finite element basis functions that look something like that for P1, then the support of that function, let's go into glorious technicolor, is this set here. Right, so the support is a subset of the domain. And if this is a compact support as a set, which is another one of technical terms, which for our purposes is essentially equivalent to being a bounded set, so a set that I can draw a circle of finite size around, then and that set is in the interior of the domain, so I don't rely on touching the boundaries in order to do it, then we call that a function of compact support. So, and that's important, and that equivalently means it vanishes, it goes to zero at the boundary. That's an equivalent definition. Now, these are the functions of compact support that are really interesting in finite element land. And the main reason they're interesting in finite element land is because they get us a lot of computational efficiency. Because it means that the matrix systems that we end up with are very sparse. Because if this guy is here and some other function is over there and their supports don't cross, then we don't get any entries in the matrix. So that's the normal finite element reason why compact support is interesting. Compact support is interesting in analysis, in proving things about calculus, for a somewhat different reason. That's the sense in which we're going to use it now. So we're going to define a set they're calling D of omega. You've got to love maths. There just really are not enough letters in the alphabet. When they write D here, they don't mean the derivative of omega. That wouldn't really make sense, right? This is just another D. So D of omega, which sometimes is also written C infinity 0 of omega. So this is like the notation we were using earlier, right? So that's an infinity. Where we used V0 to mean the set of function spaces that vanished on the boundary. So that's a similar notation here. So this is the set of infinitely differentiable functions, functions I can differentiate as much as I like, over the domain omega, which have compact support, which means at least that they vanish as they go to the boundaries of omega. So what do these functions look like? Well, there's a lot of functions in this space, but obviously they're all very, very smooth. So what's going on is you have functions which, for example, look like this. So you can do more interesting things than be flat in the middle there. It really, really doesn't matter. The point is that they're very smooth, and then they go away and vanish in a finite amount of distance while still being infinitely smooth. And for our purposes today, the whole point of these functions is that they behave really, really well when you take their derivatives. So so there's an example that they give in the book, which doesn't actually go flat on top, which is if you set phi of x to be equal to e to the 1 over absolute value of, well, I don't need absolute value in this case because I'm squaring it, minus 1 for the absolute value of x less than 1, and 0 for the absolute value of x greater than or equal to 1. Actually, I do need that in this case because this could be a multiple dimensional x. This would still work. So what this is saying, so this defines the unit ball in whatever space I'm in, right? It defines the space of points which are less than 1 distance away from 0. So assuming I have a domain which contains that unit ball, so it's bigger than just the unit ball, then this thing is clearly 0 when I'm outside there. And then what does this thing do? So when x approaches the value 1, this approaches 0, so this thing approaches 1 over 0. So this gets very, very... am I missing something here? No, that's right. So that means that this thing is very small, very fast. So you go out there.
Okay,
No,
that's really fast.
Yeah, it does. Why have they've got this wrong in the
I
book?
think it must be minus.
Yeah, it's that. They're missing a minus. Everybody take out your pen. It's a minus sign in the book at the important point. So that, and importantly, because this is the exponent, as I take derivatives, that will still be true. So as I start taking derivatives of these, I get a polynomial out the front, and I get factors of 1 over norm of x squared minus 1 underneath, which just makes things vanish faster. And so this thing remains vanishing at this point no matter how many derivatives I take. It remains infinitely differentiable in the middle, no matter how many derivatives I take. So that's really well behaved. And so now that I've written one down like that, you can imagine that by changing variables in this expression, you can get an infinitely smooth function which is centered any way you like and has as big a radius as you like. Right? That's just a question of mucking around with factors in here. So these functions clearly exist, and they're beautiful in the sense that I can take any derivative I like and I still end up back in a nice, well-behaved space. Right? So this is C infinity, it's bounded so I can integrate it, it's in Ln for any, LP for any P. Life is just wonderful. So, as we move forward then, so that's our space of really beautifully behaved functions. Now what we're going to want is a space of functions which are only just well enough behaved that we can sensibly talk about their derivative. Right? The reason we want that is because we want to write down all these badly behaved functions and take their derivatives, right? Functions that have angles in them and so on. And so knowing things about derivatives in this space doesn't help, because you can say, okay, I can do any sort of derivative I like here, and you're going to turn around to me and say, yeah, but I want the derivative of this thing. It's got an angle on the top and at these points. So this is, in some sense, this is a good cop, bad cop story. This is good cop. This is the really well-behaved space. Now let's go to the bad cop space, which is the space of functions where the only thing I can do is integrate. So this they're calling L1. So we know what L1 means, right? L1 is all the functions such that the integral over the domain of the absolute value of the function is defined and finite. So that's L1. And L1 loc, the L1 local, is the set of locally integrable functions. So that means it's the set of functions f such that f is in L1 of K for all compact, and remember, for current purposes, you can think of compact as just being bounded. K k in the interior of omega. So this thing about only being on the interior of omega, so I can choose any space I like sidling up to the boundary but not actually touching the boundary. That's a fudge that enables your functions to become arbitrarily badly behaved at the boundary. So it means that some of the stuff we're going to talk about still works for functions that in some circumstances go infinite at the boundaries and things like that. We don't really care. It's in there so that I'm telling you the mathematically complete story. The important point here is that these are functions where if I've got my domain and I choose to consider some compact set in the domain, I can integrate these functions over that set no matter which set I choose. So they're just locally integrable. That's a really weak statement about the functions, right? You can be pretty badly behaved and still have that to be true. It's interestingly notable that all of the continuous functions are in this space. So your continuous functions have to be finite everywhere inside the domain, right? There's no way to go infinite and be continuous, except that you might go infinite when you hit the boundary. You can do that and still be continuous, right? So I can't, in my domain, I can't have a function do that and still be continuous. But maybe at the edge of my domain, I can have my function do something badly behaved. So that kind of describes a space of functions which are definitely in this space. So that's a big class, and in particular includes all about continuous finite element functions. So that's good. So now we finally get, nearly halfway through the lecture, to the guts of the argument. So this is how we start defining a sort of derivative which still works on functions which at some point don't seem to be differentiable. Now we should be happy about this because the whole story, as I keep telling you, is that we're not interested in the values of functions at particular points. So we should be really happy that while still not being interested in values at particular points, we've got a concept of a derivative that we can use for these functions. And so what we do is we are normally interested in integrating functions, and we're normally interested in integrating functions multiplied by a test function. This is the motivation for where we're going. That's the problem we're normally interested in doing. And what we'd like to be able to do is integrate the derivative of this function, multiplied by a test function. That would enable us to do the whole finite element method. So what we need is a function that we can slot in here. And what does this notation going to mean to us? Well, one of the ongoing stories is, if it behaves sufficiently well like a derivative, then we can call it a derivative, right? Like with vectors, anything that behaves like a vector, we can call a vector. And in particular, one of the motivating points for why the weak derivative is defined to be like this is if this thing really were differentiable, and this thing really were differentiable, then I could integrate by parts. So I can move the derivative from here onto here. So this gives us a motivation, right? So what if I make sure that this guy is differentiable, and then ask myself, which class of functions can I still slot in here and have the same thing happen after I've integrated by parts? So that gives us a way of giving a definition. So I'll give you now the formal definition. So let's assume, I'm going to have to move down because otherwise I'll fall off the top of the video. So let's assume that our function f is at least in L1 block omega. So we at least think we can integrate f. Then we say that g is, which also needs to be an L1 block, because we need to be able to integrate this guy as well, right, in order to do anything useful. We say this guy is the weak. So we're using the weak, the word weak in the same sense that we were using it when we made the weak equations, right? True in some sort of integrable sense. The weak derivative, which they're going to very temporarily denote dw for weak. Now, obviously, with respect to some multi-index alpha, so we can define this not just for first derivatives, but for any multiple derivative in any direction. D alpha x, so is the weak derivative d alpha x of f, so g equals d alpha f. If, and only if, the integral of g x phi x equals minus 1 to the alpha. So we get minus 1 to the alpha by analogy with integration by parts as well, right? Because each time you integrate by parts, you get a minus 1 outside the front of the operation of the integral, or I better tell myself that I'm integrating with the domain, over the domain of the original function I wanted to take the derivative of times the alpha derivative of my test function, dx, for any test function in the omega. So let's just take a deep breath and work out what we've written down there. And in fact, we'll go through this in detail, and then we'll take the break, and then we'll come back and actually work with this, and then you'll understand why this is in some sense true. So what have we said here? We've said that we'll accept g as the derivative of f if g is a function that has the same effect as f would have done if we'd been allowed to integrate the derivative of f by parts. Right, so this seems like a really long-winded way of saying I just took the derivative of f and integrated it by parts. But taking the derivative of f and integrated by parts assumes that I've got a derivative of f, and it assumes that I've got a derivative of f which is sufficiently well behaved that the normal integration by parts formula applies. So I don't know that, right? And in particular, I'm interested in cases where f is not differentiable at points. So I'm interested in cases where that's not true. What I'm saying is we can still, in some sense, in a weak sense, accept g as a derivative of f if I skip over the actual integration by parts step and I just take what I would have got if I'd integrated by parts, and I still get the same thing out. That's the statement we're...
So does this sort of work because all the surface terms in your integration by parts vanish, go to 0 because phi vanishes sufficiently quickly?
So phi vanishing sufficiently quickly is sufficient to make the boundary terms go away. Making everything inside this work still places some restrictions on what f is. So we're going to take a break in a minute, and then we're going to do some practical examples, and we're going to see exactly which sorts of functions this works for and which functions you can put in there. And that turns out to be absolutely critical in understanding which finite element spaces you're allowed to use at which points in the equations. Okay, so we'll stop there, and then we'll start again in a few minutes.